right. Hi, everyone. Welcome to the MIT Museum. My name is Jennifer Novotny, and I'm our Public Programs Coordinator here. I'm really excited that you guys chose to come and join us tonight for our first of 3 evenings in our Quantum Quandaries and Other Heavy Matters Soapbox series. Some of you may have attended some of our other soapboxes in the past. Tonight will be a little bit different, but of course, you can always expect some interesting conversation and a good opportunity for you guys to engage in the conversation. We don't want this to be just another passive talk. We want you guys to have the opportunity to get your questions asked, answered, and hopefully to dream up and come up with some other great questions as well. But before we get started, I wanted to encourage you guys to come and attend some of our other events at the MIT Museum because we care about a wide variety of topics, not just quantum physics. So hopefully you'll consider joining us for our Girls' Day coming up on this Saturday. It's our Math March Madness. So we'll be exploring mathematics and sports and trying to encourage a future generation of scientists and mathematicians. We also have, for a slightly older audience, our holography evening coming up in April, where we're going to be pulling holograms from our collection that have never been displayed before. So you might consider joining us for this adult evening. We also have our annual nautical night, where we celebrate our nautical collection. And of course, since the topic of tonight's conversation is getting into quantum physics and some other physics weirdness, perhaps, I wanted to encourage you to come and join us for the premiere of Both And, a quantum physics play that has been written in collaboration with MIT and the Central Square Theater as part of the Catalyst Collaborative. And so we'll be premiering that here on Saturday, April 15th, which is the first Saturday of the Cambridge Science Festival. So hopefully some of these other options are appealing to you, and hopefully you'll consider joining us for more events at the MIT Museum. But now let's dive on in, and I would like to welcome our moderator for the evening, Professor David Kaiser.
Any better? That sounds better. Okay, thank you. So thank you to Jennifer for arranging this and indeed a whole series of events that I'm looking forward to. I hope you'll enjoy them as well. I'm really delighted to start our soapbox series this evening with 2 really wonderful speakers, members of the MIT community. I'm very delighted that they're going to talk with us about their own work and what motivates them, and then we get to interrogate them shamelessly. So think of all the hardest questions you can think of and put them on the spot. Not really. We've asked each of our speakers to come up and present informally about aspects of their work for on the order of 15 minutes or so to get a whole swirl of ideas on the table for us. And then I'll moderate a brief discussion with them, and then it really will be open to all of us to chime in. So let me introduce our speakers. We have 2 of them. The first speaker is Professor Brad Schow. Brad is the Lawrence Rockefeller Associate Professor of Philosophy here at MIT. He completed his undergraduate degree in philosophy and English at Oberlin College, his master's degree in philosophy at the University of Sydney, and then his PhD in philosophy at New York University. He joined the MIT faculty in 2007. He's the author of many, many articles on the philosophy of physics and metaphysics in all the leading journals in the field. He's also, every single one of them I counted. He's also the author of 2 books. His first book was entitled Objective Becoming, published by Oxford University Press in 2015. His second book was called Reasons Why, published by Oxford University Press in 2016, which means I think by the end of tonight, he will have published his 3rd book, if that rate is to continue, which is pretty cool. His investigations have focused pretty broadly. He's published on the interpretation of quantum theory, on varieties of scientific explanation, and on the nature of time. Our other speaker is Paola Capolaro. Paola is the Esther and Harold Edgerton Associate Professor of Nuclear Science and Engineering here at MIT. She's also a member of MIT's Research Laboratory for Electronics, where she leads the Quantum Engineering Group. She completed her undergraduate and master's degrees in nuclear engineering in Milan, a master's degree in applied physics at the École Centrale in Paris, and then her PhD in nuclear science and engineering here at MIT. Following a postdoctoral fellowship at Harvard, she joined the MIT faculty in 2009. Her research articles on quantum information processing and quantum-enabled precision measurements that she'll tell us about have appeared in all the leading journals on the face of the planet, including Nature, Proceedings of the National Academy of Sciences, and many more. Her work has recently been honored with a Young Investigator Award from the Air Force Office of Scientific Research. So I'm really delighted to have Brad and Paula here. I'm going to ask Brad up first, and he'll talk with us about some of his ideas about how a philosopher looks at quantum theory, and then we'll have Paula talk about an engineering perspective. So, Brad.
All right. Can you all hear me? Is the microphone on? No. Jennifer, what should I do? The green light is on.
I think you're actually good.
Oh, all right. Well, thank you, David. I wanted to talk just for a few minutes about Einstein's contention that quantum mechanics is incomplete. And this will connect with Einstein's complaints about spooky action at a distance in quantum mechanics. So Einstein thought that quantum mechanical descriptions of the world were incomplete. What did he mean by that? I mean, he meant if you have some physical system, like that chair or the screen behind me, anything, and you ask to be told everything quantum mechanics has to say about that physical system, Einstein's view was that even after you'd written down everything quantum mechanics had to say about it, there would be facts about that physical system that will have been left out. That's what it would mean to say that quantum mechanical descriptions are incomplete. And an analogy I keep in mind to help me understand what this view amounts to is to think about what we all believe, or anyone who knows enough physics believes, about thermodynamics. So if you said, well, tell me everything thermodynamics has to say about the state of the air in this room, right, the answer would be something like, well, you would say that the temperature is, I don't know, 70. It's kind of a little bit chilly in here, 68 degrees Fahrenheit. The pressure is 1 atmosphere. The volume of the air in this room is so-and-so many cubic meters. But that would be the end of the story. That would be more or less everything thermodynamics had to say about the state of the air in this room. And clearly, that description is incomplete. It leaves out all sorts of facts about the state of the air in this room. It doesn't say anything about what kinds of molecules make up the air, how many air molecules there are, where each one of them is, how fast they're moving. All of that information is stuff that the thermodynamic description leaves out. And Einstein's view was quantum mechanics is like that. Even if you know everything quantum mechanics has to say, there's information you're missing. Now, this is connected to the fact that in quantum mechanics, you can only make chancy predictions for the outcomes of experiments. Right? So I could have a box. I didn't bring my props, but imagine I have a box, and I put a particle in the box, an atom, a silver atom, whatever, anything you like, and I close the box. Okay, and I say, I'm going to look in the box in a minute. What can you tell me about where the particle will be when I look? Okay, now, given what I've said, you'll probably say, well, it can't really say anything. It's not very interesting. What's more interesting is, even if you know everything quantum mechanics has to say about the state of that particle in that box, even then you can only, if things are set up right, even then you can only make chancy predictions about where you'll find the particle. Like maybe quantum mechanics will tell you, well, there's a 50% chance you'll find it on the left, a 50% chance you'll find it on the right. That's the most you could say. And Einstein's attitude was, well, the reason you can only make chancy predictions, even based on everything quantum mechanics has to say about the particle, that's because there's stuff that quantum mechanics doesn't say. There's information that's being left out. If you knew all of that, maybe you could say with more certainty where you'll find the particle. But the understanding of quantum mechanics that Einstein opposed, the standard or orthodox interpretation of quantum mechanics, it went beyond the claim that you can only make chancy predictions. And to get a grip on the other aspect of that interpretation that I wanted to say something about, we need to distinguish between two questions you might ask about the particle. One is the question I just discussed, like where will I find it if I look for it? If I open the box and look. And there's another question. Where is the particle right now before I look? Right? It's clearly a different question, but we tend to think, or at least people who haven't been exposed to quantum mechanics tend to think, the questions are going to have the same answer. The answer to the question of where the particle will be when I look is going to be the same as where is it right before I look? Because you think, well, by looking in the box, what happens is the particle reveals to me the location it had right before I looked. The orthodox interpretation of quantum mechanics, though, says that these questions come apart. It says, well, you can only make chancy predictions about where you'll find it, though it does say that whenever you look, you'll find it to be somewhere in particular, either on the left or the right half of the box, or even more specifically, like exactly where it'll be. You'll find it somewhere specific. But according to the orthodox interpretation, before you look, at least in the usual case, there's just going to be no fact of the matter as to where the particle is. I mean, maybe it'll be definitely inside the box, but nothing more specific is true as to where it is inside the box. It's somehow objectively indefinite or objectively indeterminate where in the box the particle is. It's not that you don't know where it is. There's nothing to be known about where it is beyond it's in the box, according to the standard interpretation. So that, I think, was an aspect of the orthodox interpretation that Einstein, I think, opposed even more strongly than the idea that it only makes chancy predictions. Okay, so just to quickly summarize these two ways of thinking about quantum mechanics, both parties agree the quantum mechanics doesn't say anything definite about where the particle is before you look. Einstein's idea was that's just because it's leaving out. The quantum mechanical descriptions are incomplete. It's leaving out facts about where the particle is. The orthodox interpretation says, no, to the extent if quantum mechanics doesn't say anything definite about where the particle is, that's because there is just no definite fact of the matter as to where the particle is. All right. The orthodox view is really weird. I think it's really weird. What could it mean for it to be objectively indefinite where the particle is, or for there just to be no fact of the matter as to where the particle is? The standard interpretation of quantum mechanics is asking you to think there's something defective about the question, where is the particle? You should somehow learn to just stop asking that question. But Einstein didn't just find the orthodox interpretation weird and complain about it, or he didn't just assert that he thought it was wrong. He gave an argument that it was wrong. He provided reasons why he thought everyone should agree with him that the orthodox interpretation is wrong. So I want to say something about Einstein's argument. So you have to imagine a setup maybe a little bit like the one I just had, where I was talking about this box with a particle in it, but we need to imagine that there are two boxes, each with its own particle in it. And the argument is going to proceed from some claims about the predictions quantum mechanics makes about what you'll find if you look in the boxes. And those predictions are going to be predictions that no one disputes that quantum mechanics makes these predictions. Okay, so Einstein's starting point, these predictions, that's something that he and his opponents agreed on. And there are two claims about those predictions that play a role in his argument. The first claim is a claim about what predictions you can make from everything quantum mechanics has to say about the boxes if you look in a single box. You say, well, you can set things up so that if you look in one box, say the box number 1, there's a 50-50 chance you'll find the particle on the right. The right? It's like stage right and like audience right. 50-50 chance you'll find it on the right, 50-50 chance you'll find it on the left. And the same goes for box 2. You look in box 2, you can only make that chancy prediction. And that's the first prediction. The second prediction quantum mechanics makes, if you set things up right, is a prediction about what would happen if you look in both boxes and compare the results. So quantum mechanics says, if you set the boxes up right again, that if you look in both boxes, you're guaranteed 100%, with certainty you can predict that you'll find the particles on opposite sides of the boxes. If you find the particle in box 1 on the left, you're guaranteed to find the particle in box 2 on the right, and vice versa. Okay. So that's where Einstein starts from. How does this argument from those premises proceed to the conclusion that quantum mechanics is incomplete? Well, first you need to separate these boxes, move them very far apart. So you imagine that we've got one of the boxes here in the MIT Museum, we've got to move box 2 somewhere far away. I mean, we could drive it down to Harvard and put it in some Harvard museum. We could put it on a train and take it over to some museum in Los Angeles or California, somewhere else. We could even put it on a rocket, send it off to one of those exoplanets that they just discovered, 40 light years away, okay, really far away. The claims about the predictions quantum mechanics makes about what will happen if you look in the boxes, those still hold even if you move box 2 very far away. Okay. And Einstein reasoned like this. All right, now suppose I look in box 1 and I find the particle on the left-hand side. Now I know for certain that if someone looks in box 2, they'll find the particle in box 2 on the right. And Einstein concluded from that even if no one does look in box 2, the particle in box 2 is on the right, even if no one looks, even before anyone looks. Okay. And that's a claim, actually, that his opponents, the believers in the orthodox interpretation, will accept. They'll say, well, the orthodox interpretation says that it's often the case that there's just no fact of the matter as to where the particle is. But if you know with certainty that you'll find it on the right if you look, then you can say, even before you look, it's on the right. So that first conclusion he reaches, that's not one his opponents disagree with. It's the second one that they're going to start complaining. So Einstein says, well, look, after I look in box 1, I know the particle in box 2 is on the right. Furthermore, when I looked in box 1, my looking in box 1 didn't in any way influence or disturb box 2. It had no effect on what was going on in box 2. Why is that? Well, box 2 is 40 light years away. Now, maybe doing something with box 1 can disturb what's going on in box 2 40 light years away, but that influence is going to take a while to get there. After all, it would take a light 40 years to get there. So at least in the short term, at least immediately after I look in box 1, I can know that box 2 is in the same state it was before I looked in box 1. Okay, so if box 2 is in the same state right after I look in box 1 as it was right before I looked in box 1, and after I look in box 1, I know that the particle in box 2 was on the right, it follows that before I looked in box 1, the particle in box 2 was on the right. And if you accept the reasoning that's led to this conclusion, Einstein's got you where he wants you. It follows that quantum mechanical descriptions are incomplete. Because remember, the original quantum mechanical description of the boxes as they were before anyone looked in either one of them, that was a description that said there's just no fact of the matter as to where the particle in box 2 is. And Einstein said, well, maybe that's what quantum mechanics tells you, but that just means quantum mechanics is leaving out the fact that the particle in box 2 is on the right, which was the conclusion he'd reached in his argument. Okay, so that was Einstein's argument that quantum mechanics was incomplete. It didn't convince anybody. A couple decades after he published it, the physicist John Bell started thinking about it. And he got very focused on this assumption Einstein made that when I look in box 1, I don't in any way change box 2. This came to be called the assumption of locality, the locality assumption. It's the assumption that nothing I do here can immediately, instantaneously affect things that are happening far away. The only way for something I do here to affect things that are happening far away is for it to affect things nearby, and for there to be a chain of causes, each of which is near its effect, and for that to propagate out to that distant thing, and that process is going to have to take some time. That was Einstein's locality assumption. Now, if Einstein is right, the quantum mechanics is incomplete, then there must be some more complete theory, you could replace quantum mechanics with or supplement quantum mechanics with. And that more complete theory, since Einstein was assuming that the world is local, that more complete theory would be a theory in which this assumption of locality was true. So that's sort of what you would conclude if you agreed with Einstein. You would think, my job is to find that theory. What Bell proved a theorem. He proved that given a couple of seemingly innocent assumptions, there cannot be a local theory that reproduces the predictions of quantum mechanics. No local theory, given certain assumptions, can reproduce the predictions of quantum mechanics. That's Bell's theorem, and it's pretty shocking. It seems like Bell's shown, if you accept his theorem and accept his assumptions, he's shown that what Einstein called spooky action at a distance, that what I do right here in this room can immediately and instantaneously and directly affect things that are happening far away, 40 light years away, arbitrarily far away. That's true. That is the way the world works. So if Bell's right, Einstein was wrong to assume that locality is true when he was arguing that quantum mechanics is incomplete. And moreover, the standard way of understanding quantum mechanics seems to accept this idea that there is spooky action at a distance. Like the orthodox interpretation seems to say, when I look in box 1, before I look in box 1, there's just no fact of the matter as to where the particle is. But the instant I look in box 1, immediately the particle in box 2 acquires a definite position. OK. So I don't have much time left. In fact, I'm probably over time. But I'm just going to conclude with a couple of quick thoughts. One thing I think is important is to distinguish between Einstein's conclusion, quantum mechanics is incomplete, and his argument for that conclusion, which relied on the locality assumption. Bell may have showed that Einstein's argument was bad, but that does not mean that he showed that Einstein's conclusion was false. You can have bad arguments for true conclusions. And in fact, people have developed alternatives to quantum mechanics, or interpretations of quantum mechanics, they're usually called, which do attribute definite positions to every particle at all times. So those interpretations of quantum mechanics, if you think they're right, you will agree with Einstein. Quantum mechanics, as usually understood, is incomplete. What's interesting about these alternatives to quantum mechanics, or other interpretations of quantum mechanics, is they make the same predictions that quantum mechanics makes about the outcomes of any experiments we've done or are likely to do. And this is a puzzling situation to be in. What should you do when you have many theories which make all the same predictions? What should you believe? Which one of them should you believe? Should you think, well, I should be agnostic. I should think they're all equally likely to be true. I shouldn't believe any one of them more strongly than I believe any of the others. You might have that attitude. Or you might think, well, even though they all make the same predictions, somehow one of them is more worthy of our belief than the others. There's some principle by which you can select one theory as more worthy of belief than another, even if they make the same predictions. You might have that attitude. Now, sociologically, what's interesting, I mean, I don't know much about the sociology here, but the impression I get is that the community of physicists continue to believe the orthodox interpretation in the face of the fact that there are other interpretations of quantum mechanics that make the same predictions. An interesting question about that fact is, well, does that mean there really is some principle for choosing theories that are equivalent in the sense that they make the same predictions, which would say you should believe the orthodox interpretation under those circumstances, and that what the physicists are doing is thereby the rational or reasonable thing to do? Or is the fact that the community of physicists prefers the orthodox interpretation of these alternatives just a sign that they're prejudiced in some way? All right, I'll just leave that question hanging as the end of my comments. Thank you.
You see immediately the difference between the engineer and the philosopher. I come with slides. OK. Very well. So what I'd like to do is to briefly, I think this is almost too, the volume too high, I don't know. I just want to briefly introduce a little bit some concept about quantum technology more generally, and I will speak mostly about quantum computers. And my perspective is, as you can imagine, slightly different from Brad. And it starts somehow like this. I just got a notification. But even if what we want to do is manipulate information, so this is what a computer, either classical or quantum, does. What it does is to take some information and manipulate it and give you some other answer, which is still information. So information is typically a very abstract concept, but for an engineer, what you need is really to encode this information in some physical system. Otherwise, how can you do a manipulation of the information itself? And so it becomes really an engineering or physical problem. And so typically, what has been done until now is to encode this information into a system which behaves classically. But really, quantum physics is a more fundamental theory than classical mechanics, if you want. And so the idea is to say, well, can we actually try to exploit the fact that physics is, after all, quantum, and trying to use the quantum weirdness that Brad has mentioned to our advantage? And as the size of the components of a computer becomes smaller and smaller, you would have a way to take into account quantum effects. And so why don't we turn them to our advantage? And really, all these weird things about quantum mechanics that you have to try to understand, or at least wrap your mind around, actually, in the end, maybe are the things which makes quantum computer really powerful. And so even if they're somehow, if you want, a headache to deal with when you try to really understand them deeply, from an engineering point of view, is actually what you're trying to exploit. So let's see some of these weirdness of quantum mechanics. So the first thing that you can try to do is really a very, very simple experiment, which will show how, when you are trying to measure something in quantum mechanics, the outcome or the measurement is going to be some random number, some random outcome. So for example, what we can do is a very simple experiment. Okay, so we use just a beam splitter, which take an initial beam. I'm in the nuclear engineer department, so I will consider a source of single neutrons. This could be as well done, for example, with photons or with light. And so I send an initial beam of neutrons, which come one by one, onto a beam splitter. A beam splitter is an apparatus which can either let the neutron go in the same direction or change the direction by 90 degrees. Okay? And it does so in a way which is somehow random. So for the moment, let's say that this is done in a random way. So that if I have two detectors, I have a 50% probability of seeing my neutron arriving here, or instead arriving at this other detector here. Okay. So if I have a quantum object, a single neutron, and I try to measure where its position, as Brad said, this question can only be answered by a random outcome of the measurement itself. So this is something which is weird in quantum mechanics. You measure something, and it's a random outcome. But is it really fundamentally weird, as I presented it? Doesn't that also happen in classical mechanics? So I have a very, very silly experiment. Let's say that I have, for the classical world, let's say that I have an explorer, okay, so Moana here, okay, and she decides to sail into the sea to see if we can find, I don't even know exactly what it was, some kind of stone or something. Okay, and so she has to sort of leave her island and decide if to go west or east. To do that, she flips a coin to decide the direction, because she doesn't really know where to go. And so she can go either west or east. And in one case, she just lost at sea with 50% probability. In the other case, she actually arrives at the island where she wants to arrive. Okay, so randomness is not just intrinsic to quantum mechanics, but even in classical mechanics, in classical physics, you also can have randomness. So, okay, random outcome of measurement or random outcome of measuring the coin side are also present in classical mechanics. So what is really weird and different in quantum mechanics? The point is that in this travel, we will find our explorer either in this direction, going, let's say, east, or in this other direction, going west. Okay. At every instant in time, she's in a well-defined position. So if I keep measuring, I will always find her in some of the two positions. Okay. I can always define very well where the position is. However, if I consider my neutron again, when I say that this beam splitter, which is like my coin flip, decide which direction the neutron will go, it is different. I'm not saying that the neutron is either here or here, but it's actually at the same time both here or here. Okay. So these are some quantum notation. So we like this weird bracket, which again, they're just indicating that either on this path, I call it 0 path, or I'm on this other path, which I call it the 1 path. And in order to get, in the end, this 50% probability here or here, I need to have 1 over the square root of 50, or 0.5, so 1 over square root of 2. And of course, I can try to find even more paths after that. And if I have this different position here, I can still have a state in which my neutron is at the same time in each one of these possible positions. It's not either here or here or here or here. At the same time is in any of these possible positions here. Okay, so this is like a fundamental difference between classical behavior and quantum behavior. Just as an aside, since possibly many of you have never seen a neutron beam splitter. Okay, so this is what it looks like. It's actually a lingot of silicon with very sharply fabricated planes. And the crystal planes themselves decide the direction of the neutron based on the scattering. And we can indeed have more blades here so that you will have more path. It becomes more and more difficult to have larger crystal for neutrons. So this is, at the moment, one of the records done at NIST. But for example, for photons, it becomes much easier to have many more paths. Typically, you use mirrors. In this case, actually, what we used was a crystal of diamond. And you have internal reflection in the diamond crystal itself, which creates all this path. It's a bit dim, but so I'm not sure you can see. But you can see a lot of crisscrossing here in the crystal. So why do we want to have many states, many superposition? Again, what we want to do is to, in the end, encode information in some physical system. And so what we can do is, for example, to try to encode some information either in 0 and 1, which is a classical bit. For example, a circuit which is open or closed, and we assign open to 0 and closed to 1. Or we can use quantum bits, again, 0 and 1, just with this weird bracket to indicate that they are quantum. And for example, there could be a two-level physical system which can be pointing up or down. For example, my path going up and my path going horizontal. So these are two possible states. The main point is that for classical bit, my circuit can either be closed or open, but it's not going to be closed and open at the same time. While for quantum bit, they can actually be in this so-called superposition state, in which we are really both 0 and 1 at exactly the same time. Okay. Then if you measure something, okay, I will not get out this superposition here. I cannot really measure that. What I will get out is either 0 or 1 with a probability which is given by the square of this coefficient here. So probability of 0 will be a square. What do you think is the probability of being in 1? Perfect. So it's b squared, which is supposed to be 1 minus a squared. Very well. So this is for 1 bit or 1 qubit. And I have 2 parameters which indicate what is the state. Until now, not much has happened. But what I can do is then to look when I have more than 1 quantum bit, or so-called qubit. If I have 1, as I said, I need 2 parameters to determine what is the state, A and B. But if I have 2, now they can be in 4 possible different states, with 0, 0, 0, 1, 1, 0, 1, 1. Also, classical bit can have this combination, but they can only be in one of these 4 states at a time. Instead now, what I can have is also a superposition state. And some of these combinations correspond to this entangled state that we already discussed, which really also identify correlation among the 2 possible qubits here. And so here I need 4 parameters to describe the state. Now let's say that I consider 3 qubits, so 3 of these quantum 2-level objects. How many parameters, how many possible states do you think that I can have? 8. Okay, so I can have 0, 0, 0, 0, 0, 1. So there are all the possible combination. Okay, so it's 2 to the cube, which is 8 possible states. I need 8 parameters. And now what I have is only 3 physical systems, but I can encode 8 bits of information. So you start seeing how quantum systems are much more powerful than classical systems. So I need 3 systems to encode 8 bits of information, but I would need 8 classical systems to encode the same way. And of course, it keeps going. So if I have 10, I have 1 kilobit of information using my 10 qubits. If I have 20, I have 1 megabit of information. So it's megabit, not megabyte, so it's a bit less. But you can see. And if I have 40, I have 1 terabit of information. Okay. So which means that I can encode a lot of information, and I can process that information onto this much larger possible number of states at the same time. So I'm really having a lot of advantage because this allows me to really do a lot of computation in parallel. Okay, so I have all this amount of possible states, and each of them can make a computation. Instead, if I have a classical computer, you will have to make that computation one after the other, and so I will really need 2 to the 40 different classical systems in order to do the same computation in the same time. So I have an exponential, if you want, speed up in my resources. However, we haven't looked at all possible quantum weirdness. So there are some additional quantum weirdness which sort of either sort of destroy this dream of doing this computation in parallel, but then bring it back. So what is the first one? So let's say that I have a classical computer. How does the computation work? I have a string of inputs, and then I will have a string of outputs. So these are bits, 0 and 1. Okay? I input some bits, and then I will output some bits. What about a quantum computer? Even in quantum computer, I will input some classical bits, because we are human, we think in terms of classical things, and so I will still have some classical bits as my input. But then the calculation inside this quantum computer is actually done on these quantum bits, which are called qubits. And so it will be done not just on the bits, but also on superpositions of my quantum bits. So a superposition like this one, which is one of these Bell state that has been discussed before, or even for larger systems, so 3 qubits, 4 qubits, and so on and so forth. And so this computation itself can be done much, much faster than the classical one because of its parallelism that we just saw in the slides before. Okay? The problem is that when I try to measure things, I cannot really measure this superposition, and so I cannot also measure this other one. If I measure something, I will get out either 0, 1, 1 or 1, 1, 0. I cannot know both of them at the same time. This is the so-called state or wave function collapse in quantum mechanics. It's another weirdness of quantum mechanics. So out of the computation, I still get a string of bits, of classical bits. So even if I did a lot of computation in parallel, in the end, I can only get one result, one of these possible results of computation which I've done. And so, well, it seems that I'm losing all the power of quantum computers here. Okay, I can do a lot of computation in parallel, but I get only one answer out. Okay, so it seems that there is really no increase in the number of outputs. So what can I do to try to solve this problem? Let's go back to my example of the explorer. Okay, so I had my explorer. She flipped the coin, decided to go either north or south, or east or west. But after a day of travel, she was still like in the sea with no island in her sight. So she decided to flip the coin again and try to decide for a new direction and hope that this will actually bring her to either the island. So she flips the coin again, and based on that, she decided to go more north or flip back on south or the opposite. But then again, she can only arrive in these two places. And again, the probability of arriving at the island is 50%, and the probability of being lost at sea is still 50%. So nothing much has changed. The probability are still more or less the same. What about my quantum system, a quantum explorer, which I took to be a neutron? Okay. So I can replace the detectors here with some mirrors so that I can increase the number of paths. And then add a second splitter, which is another flip of the coin. Okay. This will create more possible paths, or like in the same way as the explorer, so to bring me back into a possible previous direction. But there is a difference. Here, again, my possible states are not multiplied by the probabilities of being in either 1 or 0, but they're multiplied by the square root of a probability. And in quantum mechanics, that number can even be a complex number, or more simply, for example, it can have a minus sign in front of it. Okay. So we can arrange how this operation, the beam splitter and the mirror, behave on our neutron, so that when they are recombined together, I actually only have 100% probability to arrive at one detector and 0% probability to arrive in the other one. That doesn't happen all the time. I need to set up my experiment, or if you want, my quantum computer in a particular way, Okay, so I should be able to program my quantum computer in a way so that the final answer which I get is actually the one which I want. So in some sense, quantum mechanics allow you to always arrive to the happy ending, to your island. Okay? So if you're able to program your quantum computer, to program your interferometer, you're always able to arrive at the final correct answer, the island. So really, there are two ingredients which give the power of quantum computers. It's not simply superposition, which give you this massive parallelism, which allow you to compute things much, much faster. But you also need this other ingredient, which is the interference between different states, which allow you to select the correct answer as the one that you will read out when you do a measurement which will collapse your state into one of the possible superposition parts. So these two together really give this exponential speed up of the computation. So as I said, we can do things exponentially faster in quantum computation, but you need to be able to program your computer in such a way you do get out the correct answer. So not all possible algorithms are allowed to be programmed in a quantum computer so that you do get this exponential speed up. So only some of them are amenable to this, particularly if you want a nice programming that you get the correct answer. But when you do get a very, very large advantage. So when does this advantage could be beneficial for what type of application? So for example, one of these is database search. So you look into your phone book. I mean, you don't do it anymore, but this was the classical example when quantum computers were first proposed. You look into your phone book, and if you're a classical computer and you had to search for one person, you would just start alphabetically and just look through all possible entries. A quantum computer can do that much, much faster. So this can have application, for example, in bioinformatics or even like a Google search. Another possible algorithm is the factorization in prime numbers, which sounds just like a mathematical application, but actually is at the base for a lot of cryptography. And so being able to factorize large numbers could break current cryptographic codes. So it's another very important application. You might be able to do some physical modeling. Okay, for example, reduce a very complex problem like climate, economy, engineering problem, and put them in the form that a quantum computer might be able to solve, particularly with some form of annealing. You could be able to simulate other quantum systems. So quantum systems are very complex to be simulated for the same reason that you need this large amount of information to encode the quantum system. It also means that if you try to use a classical computer to simulate a quantum system, you will need an exponential amount of resources, an exponential number of computers if you want. So you can use a quantum computer to simulate a quantum system, and it will be much faster. And this can have application in chemistry and, for example, material science, and so on and so forth. And there are also other applications for secure communication and precision measurement. In particular, I'm working on some of these precision measurement. So why don't we have quantum computers everywhere? Okay, so we sort of have understood as physicists and engineers how quantum computer can give this exponential speed up and this kind of benefits. But what we want to do is also to have a physical quantum computer based on some particular physical system, be it neutron, photons, atoms, spins, et cetera, et cetera. The problem is that quantum states are extremely sensitive to any outside perturbation, to noise. And so their quantum property tends to disappear as soon as they interact with any external perturbation. This is sort of why we don't see a so-called Schrödinger cat, so a cat which is at the same time alive and dead, which was a famous thought experiment of Schrödinger, because the larger the quantum system, the faster this decay of its quantum property into just classical property happen. And so to build a quantum computer, we want to build and control and preserve the quantumness of larger and larger quantum systems, and this becomes more and more challenging. So this is difficult, but at the same time, the fact that quantum systems are extremely sensitive to any external perturbation led us to think about the fact of using them as quantum sensor. Okay, so if we are very good at picking up any random disturbance, well, let's use them as sensor. Maybe we also get an advantage. And indeed, we have an enhancement in the signal-to-noise ratio that you can have of a sensor on the order of square root of n. So if you have n classical sensors, your signal-to-noise ratio typically improves as square root of n. But for n quantum sensor, your SNR will improve as n. So you have quite an advantage. So one thing that I'm actually working on, and I'm also going over time, so I will conclude rapidly, is actually to try to build a magnetometer, so a magnetic field sensor based on spin. So spin is an intrinsic quantum property that all fundamental particles have. And in particular, what we are using is the spin of an electron. So in the same way that a compass needle will align with a magnetic field and will move if you move a magnetic field around it, also the direction of an electron spin will also move responding to an external magnetic field. And so we can detect this movement and use the electronic spin as a sensor for the presence of magnetic fields. And actually something similar, it's already used in a technique that you might be familiar. So if somebody here has done an MRI, you've been using the same property of spin, in this case, typically of proton spins. Okay, so all the spins which are basically in water, which compose a lot of our body. So what we want to do is really to take this technique, MRI, magnetic resonance imaging, which if you want is a technique which is based on quantum mechanics, because spins are quantum mechanical properties, but I would call it quantum 1.0. Okay, so the first version of quantum, like, for example, laser, are based on quantum mechanics. But again, by now we are used to it, and we are not exploiting the most weird fact about quantum mechanics. What we want to do is really to exploit even more weird property of quantum mechanics and build a quantum 2.0 version of this type of detectors, in which we are able to really look at proteins, not as a large ensemble of million and million proteins, but look at single proteins and try to identify atom by atom what is their structure. And also, instead of looking at the brain and looking at just a millimeter-sized feature in the brain, we want to be able to look at the individual neuron, again, using this novel quantum sensor based on the electronic spin. The electronic spin that I'm talking about is actually a defect which you can find in diamond. And it's a defect which gives a pink color to diamond. So if I had this gem, I would be very, very happy. Typically, we don't use this, as you can imagine. We just use like small diamond chip, synthetically grown. But the fact that it gives color, so it emits light, allows us to really see individual electronic spin inside the diamond itself. And we use this fact to be able to look at a single electronic spin and its connection, its interaction with external magnetic field. So one of the things that we would like to do is to use our electronic spin to look at other spins, like water in a protein, to identify the structure of the protein itself. OK, I'll leave you with more of the things that we do in my quantum engineering group, and I will stop here. Bring back your computer.
This might work better. OK. So thank you both to Brad and to Paolo. That was a fantastic tour. We covered an enormous range of ideas and topics and devices. I want to make sure we have time for questions from all of you. I have a bunch of questions that I can talk with them about basically all night, but which I might subject them to. But I want to make sure we have a chance for you to ask some questions as well. So if anyone has a burning question they want to launch into, please feel free. Jennifer might try to come to you with a microphone, or I can just repeat your question to make sure everyone can hear it. So does anyone want to jump right in before I start interrogating them? Yeah, Michelle. you want to just repeat the question? Yeah. So, very briefly, Michelle was asking Brad to describe his interest in time and the philosophy of time and how that intersects with other philosophical interests, either about quantum theory or more broadly. So, sure, your first book was all about trying to understand time.
Yeah, I really like that. I like people to say that, my first book.
You got 2 out, right? So you got to count them somehow.
Yeah, I could talk about that for a long time. I guess I try to keep it kind of brief. One of the questions philosophers ask, believe it or not, is there really such a thing as the passage of time? Is the passage of time a real phenomenon? Okay, it sounds like a dumb question, like the answer was obviously yes. Unless you're some crazy Buddhist who thinks somehow it's all an illusion. Part of the reason philosophers ask that question is if you look seriously at what physics says about time, especially theory of relativity, not so much quantum mechanics, theory of relativity, it makes it look like, well, like from a God's eye perspective, the past, present, and future are all laid out already, and there really isn't anything that would correspond to the passage of time. In fact, part of this connects up with the idea, well, if there's such a thing as a passage of time, there must be such a thing as the way the world is now. This must be a fact of the matter about what's happening on the moon now, what special relativity is supposed to teach us. There really is no objective facts about what's happening on the moon right now. This notion of simultaneity is the best relative notion. And so philosophers have taken that to put pressure on the idea that there really is such a thing as the passage of time, the passage of time looks like it requires some notion of absolute simultaneity. So part of my work on the philosophy of time is to try to navigate through those issues. And I'm on the side of the people who think, as they say, there's no such thing as the passage of time, misleading as it may be to say in non-philosophical contexts, and try to explain away why it might appear that there is. So that's sort of what I write about.
I'm going to take Chair's prerogative and build on that for a second. Actually, a question for each of you. Now this is really on. And I wonder if you could think back when you first began encountering some of these weirdnesses, either about relativity and the passage of time or about the quantum phenomena that we heard about. Can you remember what it was like when you first began kind of tripping on these ideas that seem not to follow our ordinary intuitions? At least don't follow my ordinary intuitions. And what was that like? Was it exciting? Was it terrifying? Was it already kind of banal because everyone seemed to know that? What can you get back to your former self? Speaking of a passage of time, when you began encountering some of these sort of delightful weirdnesses, quantum mechanical, relativistic, or otherwise. How did that put you on a path that led you to here at MIT and the MIT Museum? Was that not so surprising in hindsight? What do you think? Maybe I'll start with Paula and then come back to Brent.
Yeah, so I think that when I first started quantum mechanics, it was definitely weird. So I think that now I have this acceptance quantum mechanics, so I'm not sure if I understand it deeply, but it's like, okay, I use it every day, and so there are things which are automatic. So the idea that you have a superposition, yeah, it's fine because you can always measure in some other basis, and then your result is definite. So there is some concrete meaning for me what a superposition is. But when I started thinking about it, it was like, okay, so you might be here and there at the same time. What does that really mean? It doesn't really correspond to anything that you can experience directly with your senses. And so it's really puzzling. At the same time, because it's puzzling, then you're like, oh, okay, I really want to know more about it. And I think that's what sort of started me toward, okay, really something that I want to learn more about.
So you've gotten to a point, it sounds like, where you can sleep at night, which is good, right? We want that for basic health. But there's still a kind of, it sounds like, Paolo, there's still, when you can pause and sort of come up for air in between grant writing cycles and teaching your classes and all the things that keep us busy, but there's still a basic weirdness there. The weirdness hasn't bled out, right? But although it might have become more, you're used to it maybe.
Yeah, I still teach the fourth undergrad class in quantum mechanics for nuclear science and nuclear engineer, and so it's still every year brings me back to try to put myself in somebody else's shoes who see this. Somehow, for the first time, people sometimes come with already preconception, and so I try sort of demystifying some of the preconception and trying to make it at least a bit accessible, while at the same time keeping the mystery, because I think that having some of the mystery is really what pushes you to keep doing experiments, keep understanding better, and so on and so forth.
Brad, how about you? Can you remember a time that seemed new and weird instead of just weird?
I don't know. I think actually I understand the weirdness of it more as time goes on than I did when I first encountered it. I think, as I've been trying to think of what I might say, there's maybe two aspects to that. First is, like, maybe I first got exposed to some of the strangeness of quantum mechanics like early in life, like in high school. You take chemistry and you learn about electron orbitals, and they tell you we're not supposed to think that the electron's like moving around the nucleus in the same way that the Earth moves around the sun. You're supposed to somehow think of it as like spread out through the orbital or something like that. And when you're young and impressionable and your teacher says that, you sort of like, oh, okay. You think, well, that's some deep thought that I don't fully grasp, but it can't be that bizarre because everyone all the grown-ups seem to believe it. And then also, I was an English major in college and in the 90s. And I don't know what's going on in English now, but at the time, like, it was like literary critics and literary theorists were full of crazy metaphysical ideas, like, oh, there's no objective reality. It's all constructed by our readings of these texts. Like, that was another thing that was delivered down to me by the authorities at an impressionable age. And it was only after I became a philosopher and had been like studying philosophy for a while that I said, these are crazy ideas. What are these people even talking about? What could this mean? And so I guess I find it weirder now than I did originally. And like Schrodinger in his paper, he's really good about this. He says, oh, well, maybe we can make our peace with the idea that an electron is somehow smeared out through space, even though this isn't so true for life, even whenever you look for them, they're always point-sized, but somehow when you're not looking, they manage to be smeared out. But like, what would it mean to think that about a cat, that it could be somehow smeared out between being alive and dead? Like, it's just abhorrent. It doesn't make any sense. But nevertheless, like the standard way of thinking about quantum mechanics says, that's the way the world is sometimes. How could that be? What does it even mean? I don't know.
And people are pushing the boundary of what is between like an electron and the cat. I mean, nowadays people can have superposition of molecules which contain like 100 atoms of carbon, for example, like the buckyball 60, like even larger. And people are even thinking of sort of creating superposition of viruses which can survive in vacuum just because it's easier to have a like isolated system in vacuum. So maybe we'll have one day like a real superposition of a living object. And I mean, to me, I can easily accept my superposition of my electron spin, but like superposition of a living object, I'd probably be viewing still being tough to really grasp.
Thank you. Other questions from any of you? Yeah, please, right in front.
How mature is the theory of quantum mechanics? I guess what the... So how mature is the theory of quantum mechanics, and what should we expect to see breakthroughs or changes, or kind of where does that stand?
Great question. So I believe you were able to hear, how mature is the theory of quantum mechanics? Are we in for more surprises, I think is a fair summary.
This might be something that David is most qualified to answer rather than either of us.
I'm supposed to interrogate you. You read the rules beforehand, Brad. You know that, right? No, I have a few thoughts on that too, but I don't know if either Brad or Paula want to start.
There is a lot which is known, and like if you're trying to build a quantum computer, probably a lot which would go into a quantum computer is settled. But then there is, I think, still a lot of things which are puzzling, like starting from measurements, for example. And so I think that hopefully we will have more breakthrough. Yeah.
So maybe here's my 2 cents.
Yeah.
If you mean how mature is it, like how well tested are its predictions? Like it's the most well tested, most highly the scientific theory we've ever had. Its predictions have been checked and found to be correct, far more decimal places than any other theory we've ever had in the history of science. So in that sense, you might think it's quite mature. But if you mean how mature is it, how well do we understand what it's saying about what the world is like, then I think the theory is in its infancy. There are, dozens, or at least a handful, of interpretations of what the theory is saying about what the world is like, which are radically different, completely different. If I told you what one of them said and told you another, there's no way those theories have anything to do with each other. And in a sense, that's true. The only thing they have to do with each other is they make the predictions quantum mechanics makes, but they disagree radically about what the world is really like. So in that sense, and if you say, well, is there any a rising consensus by the experts as to which of these ways of thinking about the world is the right one to have if quantum mechanics is the right theory. Like, there's no consensus.
I'll just add briefly, I agree with each of these comments. And so it is remarkable that every single experimental test has been consistent with the predictions of the equations of quantum mechanics, some of them to 12, 13, even 14 decimal places. That really is just, to me, that's mind-boggling. Far more precise than tests of any other scientific theory that I can think of. Even when people design increasingly intricate kind of Baroque tests to say, oh, did we overlook some weird kind of thing over here? Well, wait, actually, even that checks out as well. I've been involved with some colleagues in some of these kinds of tests of entanglement of the ideas that Brad was describing in the beginning. But nonetheless, I think there's another way in which the theory might be, if not in its infancy, then at least maybe not a finished product. And that comes from more theoretical motivations. We've never caught it wrong empirically, and now people like Paola and her colleagues can build on its strengths to make new stuff in the world, which is a pretty impressive test as well, I think. But we also don't have any way to fit that together in a really kind of first principles way with the other great, beautiful edifice of modern physics, relativity. So relativity, Einstein's basic theory of the behavior of space and time that gives rise to things of phenomena like gravitation, that's also been tested a gajillion different ways and passed every single test, even the ingenious and Baroque ones. And yet conceptually, we just have no particular way to fit those puzzle pieces together. We have some ideas that aren't quite, haven't quite been completed yet, and they might also just be complete dead ends. So does that mean quantum mechanics ultimately has to give way to something that looks more like relativity? Is it the opposite? Is it some third way that people haven't dreamed up yet? So even while we continue to test and build on quantum mechanics with, to my mind, kind of hair-raising success on a range of scales, there's still some kind of, I don't want to call it a ticking time bomb, but there's still some big challenge out there that excites a number of my colleagues to say, can we actually answer one of Einstein's own great dreams and have a theory of nature, a self-consistent description of nature that could help us telescope not just from the electrons and the viruses and Paola's quantum sensors, but also up through, beyond the Big Bang and black holes and everything in between, and galaxies. And that really is elusive. And whether that means we have surprises coming for quantum mechanics or relativity or something else, that I think we really don't know yet. There's another area to look at, kind of fissures that might open up. Other questions? Yeah, right up front.
What's limiting the development of quantum computers now? Is it the algorithm, or what is it that limits the development?
What's the limiting factor for quantum computers these days? What's the basic limitation, most important limitation?
So I think that in some sense you're already alluding at the two limits. So on one side we have a finite number of quantum algorithms which allow this sort of programming things correctly so that you get the correct answer, which I alluded to. So like database search and factorization. People are coming up with more of them, but it still is not covering everything. So that's one limitation, if you want, which sort of what I call quantum computer science, if you want. And then there is like the software, and then there is like the hardware part. So we want to have a physical system to really run this quantum algorithm. And even there, like the limitation is the fact that we need to build, control a large quantum system so that we are really able to run this large computation. So for that, the limitation is really this interaction between your quantum system and the external environment. So any possible perturbation, be it like stray electromagnetic field, temperature variations, like even a dust, particle dust, et cetera, which makes immediately collapse your quantum system. And there are ways of trying to address this, which involve trying to do error correction. So in the same way that in classical computer, you try to correct possible errors which occur during the computation, you can do it also in quantum computers. But that sort of demand to increase the number of qubits. So if I want to have a computation done on 1 qubit, I would actually need 5 physical qubits to be able to correct for any possible error, or maybe 7 if you want to be more accurate, and so on and so forth. So then it's sort of like trying to catch something like a moving target. So you want to build a larger computer, but then it becomes more and more fragile. You need even more qubits to try to make it robust to errors and so on and so forth. At the same time, like the technological progress, I think, especially in these past few years, is really sort of improving quite a bit. And so there is the hope that maybe we will not have a quantum computer which can do any possible computation. But if you want to do like one particular task, let's say you want to simulate a chemical reaction, you might be able to do that. And this is, like, I think, quite close on the horizon, so like specific task computers.
Good. Other questions? Oh, yeah. Thank you. Right up front.
Thanks. Yeah, I'm curious, with one of you an engineer and one a philosopher, how much your fields are able to talk to one another or interested in talking to one another about quantum mechanics.
That's a great question. They're eyeing each other suspiciously. Maybe that's your answer right there. Who's going to go first? Arm wrestling, yeah.
I mean, so like, I can start since I'm speaking. I think that like, even while I'm building things, I still have on my mind this question, which are, I think, in some sense, beyond engineering, beyond physics. And sometimes I do have time to think about it, and not all the time. And these are quite interesting. There is also like part of my research which might be sort of pushed a bit more by these more fundamental questions, which are not just to find an application, but really trying to understand, for example, how a quantum system in the end becomes something which looks a classical thermodynamic system. So I think that like there are sort of like moving boundaries between what we can do, which are sometimes unfortunately set by all the commitments that we have to take care of.
Well, Ludwig Wittgenstein said that philosophy leaves everything as it is. So he was right. I mean, it's like, I don't think what the engineers, their research programs on quantum computers are, it's very strange if I marched over there and said, you guys are just making this terrible, you're never going to succeed, and here's why you're making this terrible mistake. I mean, there are episodes in the history of science of that, of philosophers doing that sort of thing. It seems unlikely to me that that is what is going to happen. I mean, there have been famous quantum physicists who've said quantum computing proves that the many worlds interpretation of quantum mechanics has to be correct. Otherwise, quantum computing would make no sense. So there have been attempts to say that, like, the success of these engineering research programs shows that one of the parties in the philosophical debates about quantum mechanics is right, the other ones are wrong. But I think he's just completely confused with it.
Yes. I think there are border regions where some of these sort of tests of quantum entanglement, say, laboratory tests, which are sometimes done to inform or in some sense shore up practical applications. So if entanglement were somehow a mirage, if the equations of quantum mechanics were leading us down a blind alley and there was some alternate explanation more akin to what Einstein had articulated or hoped for, the way Brad introduced it, then a lot of the core ingredients to things like quantum encryption and quantum computers would be suspect. Maybe encryption could be hackable, and so that could have real-world implications. At the same time, a lot of these fancier and fancier experimental tests of, say, quantum entanglement rely on technologies and devices that come from efforts like Paola's and her colleagues. So if you can really sort of manipulate single photons and ask very specific questions of them, that comes because they have all kinds of ideas they have in mind for those, and then some of those experiences in, say, precision instrumentation can come back to answer philosophically motivated questions about, is the world like that? What about Einstein's other ideas? What about rival theory number 2 or 3? And so there are meeting grounds where sometimes you will have, philosophers and engineers and other folks in between in this sort of academic Schrodinger's cat superposition, who really have a certain kind of space to try to if not debate, then at least to have a kind of borrowing. But I do think you're right. I think universities are big, complicated places, and we collectively, I think, tend to drift with a kind of disciplinary momentum more often than not. That's my impression, at least. Other questions? Jennifer has a question.
So what predictions that quantum mechanics makes are you the most excited about to see come to reality? Or perhaps maybe not come to reality, but
That's a stumper. That's good.
Okay. So one thing is this, if you want, the divide between quantum and classical worlds. So as we say many times, we cannot see a Schrodinger cat, so a superposition of a very macroscopic object. There is no real prediction of where the boundary between what is quantum in terms of size and complexity and what is classical should really be. So I don't think that there's going to be like one moment in which we can say, okay, here is the boundary. I think it's going to be more like we're going to push more and more that boundary toward larger and larger, more complex system. But there are like some people doing heroic experiments along these lines. I mean, I like great respect for them because they're very, very tough experiments. And like every time that they publish something new, I'm like, oh, they managed to, now it's no longer like 100, it's 120 atoms. And it's like, I think that's really exciting.
Maybe this is what I could say about that. I mean, it's not like I've read the Encyclopedia of Quantum Predictions, so I could have circled my favorite unrealized prediction.
You can borrow my copy if you want to.
Can I? Yeah, it's.
I'll share.
I'm sure you have one. So the standard view of quantum mechanics says, like, before you look in the box, there's just no fact of the matter about where the particle is, and then the act of looking causes the particle to choose a particular position to be in, which is insane. It's crazy. Like, certainly it wasn't the case that all the electrons in the universe were waiting around for some human to be born. Before the evolution of humans, no particle was ever anywhere, and then finally, when finally the first human arrived on the scene, then they all chose their positions when he looked around. It couldn't possibly be right. So there's one view about quantum mechanics that says, well, no, what happens is things spontaneously choose to have definite positions. It's not that looking at them causes them to, but you can fine-tune like how they spontaneously do it so that it seems to us like looking is what causes them to choose a definite position. But, so on that view, the way it's typically understood, like big things just can't be in indefinite states. Like a cat just couldn't be for very long, more than like a fraction of a fraction of a fraction of a second. It'd be indefinite whether the cat's alive or dead. And what the people who work on quantum computers do, their goal is to like put bigger and bigger systems in states of indefiniteness for longer and longer stretches of time. And the more they succeed in doing that, the more that casts doubt on these interpretations that say things localize themselves spontaneously in such a way that big things couldn't be indefinite in their position. So I guess that I'd be interested to see them build something big that managed to stay in an indefinite state for a reasonable amount of time.
I want to ask a variation on Jennifer's question, and I'll get yours as well, for both Paola and Brad. Basically, if there were some sort of friendly demon, that maybe is the wrong way to say it, there was some friendly answer giver who granted you each one answer to one question, what would you most want to have answered? Maybe it's just another version of Jennifer's question. You get one shot, you get only one question, right? Let's say. What would you? I mean, would you want to say, oh, is it the many worlds interpretation or not? What would your one question for this friendly quantum genie be like? You've always wanted to know this. The rest you can keep working on.
About quantum mechanics?
About quantum mechanics. Well, we only got so much time here, Brad. But let's start with quantum mechanics. Yeah. Right. As a quantum genie in particular.
Quantum genie.
Yeah.
Well, maybe I'd put myself in a superposition of asking him many different questions. That's like I guess that's asking for more wishes. Right?
It might be, but according to some interpretations, you'd only be able to recognize one outcome anyway at a given time. So you can't, there's no free quantum lunch there. It's gonna. Okay,
so I don't know, but here's something I think about. Like when Paola was giving her presentation, she said like the neutron hits the beam splitter, and then she said, and then it goes down both paths, right? Okay. So what she said was it contradicted what I said. The orthodox interpretation of quantum mechanics says. The standard interpretation says what happens when it hits the beam splitter is there's just no fact of the matter as to which path it goes down. You say, which path is it on? You should say, there's something wrong with that question and you're making some terrible mistake. So she was working with a different way of understanding quantum mechanics, more like the many worlds interpretation than I was trying to present when I talked about the standard interpretation. I'd like to know if the many worlds interpretation was correct. If the many worlds interpretation is correct, then you could resolve, you could stand in front of one of these beam splitters, one of the paths, and say, well, if I see the neutron, maybe it's supposed to be, you'd want it to be something bigger than a neutron, or anyway. If I see it, then I'll resolve to make my life go one way. I'll devote myself to being a concert pianist, and if I don't see it, I'll devote myself to being a philosopher. And then, if the many worlds interpretation is true, what happens is, after the neutron hits the beam splitter, is you live both lives. So I'd like to know if that is the true understanding of quantum mechanics. I'd want to do this experiment a lot, because I could live a very rich, complicated life, or many rich, complicated lives simultaneously.
Yes.
That would be interesting.
Do you have a wish for the quantum genie, Paula? No. Okay. There was a question, yes, here. Maybe one will come to you in the meantime. Yeah.
Paula, you talked about with this quantum computing, we can simulate chemical reactions and things like that. So do you think with this computing power, we can simulate or in some sense recreate human brain? And a follow-up question to that is that if at all we can do that, then we can simulate every brain on this planet and in some sense predict the future, what is going to happen. So do you think that is a possibility?
Maybe I should say that I wanted to know from the demo
the
if
price you
everything
pay.
is deterministic or if there is really free will, which sort of would answer your question somehow. I mean, again, in the same way that some algorithms work well in a quantum computer, also some quantum simulation will work well. So there might be systems which are better adapted to be simulated on a quantum computer. So when I talk about like chemical reaction, it's because fundamentally they're quantum systems reacting with each other, and so like mapping it to another quantum system might be easy. For a brain, I do not know enough about brain to tell you, yes, there will be like a quantum algorithm for which this is efficient to both encoding the information and then computing the information so that we will be able to sort of simulate a brain. There's also the question, is the brain quantum? Well, since for me everything is quantum, so also the brain should be quantum, but there is some limit. In terms of the future, probably even for a quantum computer, there are limits. So there are classes of problems which are still hard on a quantum computer. So like there are problems for classical computer which will take an exponential amount of time to solve. And some of these problems takes only like a linear amount of time on a quantum computer, but there are even harder problems that are still exponential in the number of resources that you would need on a quantum computer. So I have no reason to say this, but I'm sort of thinking that probably predicting the future is something which is going to be an exponentially hard problem even for a quantum computer. As much as I can guess there. But.
It's a question here. You can. I'll repeat it if you want to. Yeah.
So my question has to do with what you were saying earlier about like the particle isn't waiting around for a human to observe it, right? So if that's the case, then kind of what counts as an observation? Can a particle observe itself, or is it not really a particle, and like can it still observe itself with whatever it is?
So the question was, at least in brief, what counts as an observation within quantum mechanics? We very casually say the particle has no definite state until I open the box and make an observation. The cat is neither alive nor dead. It's both alive and dead until I make an observation. So what counts? What's sort of the limiting case of what could count as an observation in quantum theory? It's a great question.
I mean, I guess what I would hope, I think this is what John Bell's view was that you just would not have to answer that question. So if your theory, if you're working with a version of quantum mechanics that says the way things behave is different when they're being observed than when they're not being observed, which is a common way of understanding quantum mechanics. Things jump around when you look. Then, of course, you need to say, like, when is someone looking? Like, is it enough for a lemur to be looking at it? Does the person looking have to have a PhD? I feel like it would really be much better if your physical theory didn't require you to have answers to these questions to be able to figure out what you thought was going to happen. So my hope would be that you wouldn't need to say anything particularly informative about that because it just wouldn't be true, fundamentally speaking, that the way things behaved depended on whether someone was observing them or not.
Yeah, go ahead.
Richard Feynman.
Yes.
He once said that once you make an observation, you change the course of the state.
Yeah.
So
there was no true observation.
So the comment was Richard Feynman, a fine MIT alum, we're very proud of Richard Feynman, had said once that once you perform an observation, you change the system being studied. And so, so what does that mean for the future of that system, or what does it mean for the nature of observation, I think is the gist of the comment. Yeah.
I mean, so from my perspective, like going back to the observation, for me is you have your system and then you have another system, and the observation is nothing else than an interaction between the two. And so you don't really need like a sentient being to make the observation. Just the fact of that interaction is sort of exchanging information between these two systems. Now, of course, what I would take is my first system to be quantum, and second system, my measurement apparatus also to be quantum. But then at some point, I would like to translate it into something which my brain can understand, and understand mostly classical mechanics. So in some sense, the system which is observing becomes larger and larger. So let's say that I start having like a photon and I want to measure where it is. I will make it interact with an electron. And so I can still consider the electron is quantum, but then it will cascade into multiple electrons. And then it becomes more and more difficult to isolate this sort of growing measurement apparatus, which are all interacting. And they are no longer interacting only with each other, but also with the rest of the world. And that sort of somehow decide in which state they will be. And so it's sort of like an imperfect change. So you could think, okay, I start with a quantum system and measure with the quantum system, nothing has changed. Measure with another quantum system and so on and so forth. You could go on forever. But somehow along the way, this interaction with all that is external to this quantum system sort of decide in which direction they're going. So it's not a very good answer. I know that like this still leaves some open question, which to me are very, very interesting, which is like this measurement problem. But it's a direction to try to understand where maybe the answer could be looked for. And people have indeed tried to do experiments along these lines to see how this quantum measurement apparatus can indeed induce this collapse of the system toward a well-defined state.
I think that's, I hope for the future is a fine point to end on, so I think Jennifer has some announcements, yes? Okay.
Fantastic. Thank you guys. Let's give all of our presenters a huge round of applause. So I passed out a survey, so if you guys could take a quick minute to fill that out and then turn it into Amanda over there. If you put your name on the bottom of the survey in about 3 minutes when everyone turns it in, we're going to do a quick drawing for 101 quantum questions. So to perhaps keep spurring your conversations or thoughts about quantum quandaries and maybe helping develop and answer some of your own questions. So if you can just take a quick minute, fill that out, and turn it into Amanda, and then we'll do a drawing. While those of you who have filled it out, I do encourage you to come join us next Tuesday. We'll be moving to a slightly larger scale where we'll be looking at the Higgs boson and neutrinos. So hopefully the same types of questions, the same types of conversations, but with a slightly larger system. So let's just take a quick minute, turn it in, and then we'll do a drawing. Thank you guys for joining us tonight.